Good afternoon to all. Yesterday we learned half adder and full adder circuits. Today we will continue that topic again here. So yesterday we have studied the half adder and full adder circuits, their action. So half adder circuit is used to add two binary digits which produces a sum and carry. So to add two binary digits, half adder circuit is sufficient, but to add three digits, a full adder circuit is required. So we have seen the half adder as well as full adder circuits along with its truth table we have seen. So this is the full adder logic circuit with its truth table. This is the symbol of full adder which adds three digits. So the third digit is the carry produced by LSB or higher columns, addition of higher columns. So this carry input is again added into the 2-bit addition. So 2-bit addition A and B is done by this half adder 1, and the carry sum produced is applied to the second half adder to which there is a carry input. So this full adder circuit accepts the carry input. This full adder circuit accepts the carry input. So this carry input and the sum of the full half adder 1 is applied to the half adder 2. So half adder produces half adder 2 produces final sum, and this OR gate produces final carry. Now we can understand the working of this circuit by taking the values of A, B, C from this truth table. So we have seen all these things yesterday. Now let us move further. The full adder circuit can also be constructed by another method, and that another method is called as the sum of product method. This method is called as the sum of product method. So if you are able to see this truth table, see in this truth table, suppose this is A, B, C. So A is equal to 0, B is equal to 0, C is equal to 0. So the output is 0 because the sum of A, B, C is 0. So taking these values, taking these additions A, B, C, this is the output sum, and this is the carry producer. So we can build or we can design the full adder circuit using this another method known as sum of product method. Sum of product method. So this is the sum of product method. So full adder is a circuit which is used to perform addition of 3 binary bits. Now we have seen already. The full adder accepts 2 inputs bits and input carry. So A and B, these are the inputs, and C is the carry, and generates 2 binary digits on its output. So it generates 2 binary digits at the output, and one bit is called as the sum, and other is called as the carry bit. But this it accepts an input carry. So it can be designed with the help of this truth table. So here, see in these dotted lines, how to design a full adder using a sum of product method. Sum of product method. Now this is the truth table. हे truth table बघा, या truth table कडे लक्ष द्या. आता हा जो पहिला कॉन्स केलेला आहे डॉटेड लाईनचा, हा डॉटेड लाईनचा, इथे हा A is equal to 1 आहे, B is equal to 1 आहे, त्यावेळेला कॅरी किती आहे 1 आहे. कॅरी किती आहे 1, राईट. नंतर कॅरी 1 कुठे कुठे आहे ते शोधायचं. समजा हा कॅरी 1 आला की नाही, हा कॅरी 1 कुठे येतो, when A is equal to 1, B is equal to 1, कॅरी 1 आहे. दुसरा कॅरी कुठे आला आहे, हा आलेला आहे. तर तो केव्हा आहे, वेन ए इज इक्वल टू 1 सी इज इक्वल टू 1. म्हणजे वेन ए इज इक्वल टू 1 सी इज इक्वल टू 1, तर त्यावेळेला कॅरी 1 येतोय. नंतर पुढचा कॅरी कुठे मिळतो आपल्याला, बी इज इक्वल टू 1 सी इज इक्वल टू 1. बी आणि सी ला कॅरी मिळतोय. आणि शेवटचा जो येतो तो ए बी सी 1 आहे, त्यावेळेला आपल्याला कॅरी 1 मिळतोय. सो वी गेट द कॅरी बिट 1 when AB is 1. So take the product of this, take the product BA. So the first product is BA. So 1 into 1 is 1. So carry is equal to BA. Now the next carry is obtained for CA. So take the product of CA. So this is the CA. And third carry is obtained for CB. So take CB. So product is CB. And the last carry is obtained for A, B and C. So for A is equal to 1, B is equal to 1, C is equal to 1, the carry is 1. So last is CBA. So this is the product of B and A. This is the product of C and B. This is the product of C and A. And this is the product of A, B, C. So, this dotted line shows the output carry high when this product is high, this product is high, this product is high, and this product is high, or its value is 1. म्हणजे ज्या वेळेला या प्रॉडक्टची व्हॅल्यू 1 असेल, BA ची व्हॅल्यू 1 आहे, CB ची व्हॅल्यू 1 आहे, CA ची व्हॅल्यू 1, CBA ची व्हॅल्यू 1, तर त्यावेळेला आपल्याला कॅरी काय मिळते, वी आर गेटिंग द कॅरी 1. त्यावेळेला आपल्याला कॅरी 1 मिळते. बरोबर. म्हणजे या ठिकाणी दिस इज द प्रॉडक्ट. सो प्रॉडक्ट आपल्याला माहिती आहे की हाऊ टू ऑब्टेन द प्रॉडक्ट. सो प्रॉडक्ट कॅन बी ऑब्टेन बाय अँड गेट. कारण अँड गेटचं आउटपुट काय असतं, ए डॉट बी. बरोबर, इट इज द प्रॉडक्ट. आणि आपल्याला या सगळ्यांची काय करायची, शेवटी सम करायची. सो म्हणून आता इथे हा ए बी सी, हा इथे सी ए, सी बी आणि सी, तर या तिघांमध्ये ए बी सी येऊन गेलेलं आहे, ए बी सी आलेलं आहे. त्याच्यामुळे आपल्याला सी बी ए सेपरेट घेण्याची काही गरज नाही, बिकॉज इट विल बी ऑलरेडी देअर. म्हणून बुलन इक्वेशन काय होईल, कॅरी इज इक्वल टू बी ए प्लस सी बी प्लस सी ए. म्हणून याचं नाव, म्हणून देअरफॉर दिस मेथड इज कॉल्ड ॲज द सम ऑफ प्रॉडक्ट मेथड. सम ऑफ प्रॉडक्ट म्हणजे आता बी ए, सी बी अँड सी, दीज आर द प्रॉडक्ट्स, अँड कॅरी इज इक्वल टू सम ऑफ द प्रॉडक्ट्स. या सगळ्या प्रॉडक्टची आपण काय केली आहे, सम केलेली आहे. बरोबर. सो कॅरी इज इक्वल टू सम ऑफ प्रॉडक्ट्स and sum is equal to A, B and C. आपल्याला sum is equal to A, B, C. So these are the A, B, C. यांची आपण sum इथे सेपरेट घेणार आहोत. So sum of, so by this method, sum of product method, आपल्याला बघा मागच्या याच्यामध्ये आपण एक ऑर गेट आणि एक्सक्लुझिव्ह ऑर गेट वापरून आपण सर्किट बनवलं होतं. आता या ठिकाणी काय वापरलं आपण, 3 अँड गेट वापरलेले आहेत. यूज द 3 अँड गेट्स. आपण 3 अँड गेट्स, हे 3 अँड गेट्स वापरून या तिघांचे आपण ऍडिशन करणार ऑर गेटने. सो दिस इज द ऑर गेट. बरोबर. सो सी हाऊ ए बी सी आर कनेक्टेड. म्हणजे ए इज कनेक्टेड टू अँड गेट फर्स्ट, बी इज कनेक्टेड टू अँड गेट फर्स्ट. नंतर म्हणजे अकॉर्डिंग टू दिस प्रॉडक्ट बी ए, म्हणजे बी अँड ए आर कनेक्टेड टू अँड गेट. नंतर सी बी, सी अँड बी, C and B are connected to the AND gate. So C and B are connected to the AND gate. Third, and CA. So C and A are connected to the AND gate. And the output of the AND gate is ORed. त्यांचा आउटपुट आपण काय केलं, OR gate ला अप्लाय केलं. So this is the OR gate, and this will produce the final carry. This produces the carry. And the sum of these 3 bits is carried out by this exclusive OR gate. So this is the 3 input exclusive OR gate. This is 3 input exclusive OR gate. So put the values here, A is equal to B is equal to A, B and C. Putting the values of this A, B, C here, you can check out what is the sum and what is the carry. Now take one example. Suppose I want to verify this third condition. Suppose this third condition I want to verify. So in this third condition, C is equal to 0, B is equal to 1 and A is equal to 0. So sum is equal to 1 and carry is 0. Now apply C is equal to 0, only B is equal to 1 is there. So B is equal to 1, so this is B, and all A and C are 0 0, so A and C are 0 0. So the sum is 1, because this is the exclusive OR. So sum is 1. But what is the carry? Because A is 0, B is 0 and C is 0. So the product is 0, and therefore the carry is 0. And therefore for this third condition, sum is 1 and carry is 0. So we can verify all these things by putting these values A, B, C as for this from this truth table. So this is the symbol of full adder. This is the symbol of full adder. So this it has 3 inputs, A, B, and C. So C input is C input accepts the carry. C input accepts the carry, and it produces the sum and the final carry. So this is the symbol of this full adder circuit. Let us move to the next. So this is a 4-bit binary adder. How to add 4 bits simultaneously? You remember there is not necessary to explain the function of this circuit. You see how the 4-bit numbers can be added by connecting 1 half adder and 3 full adders. So 4-bit, 1011 plus 0111. These numbers we want to add. So how these numbers are added? So take 1 half adder and remaining full adder. So remainings are the full adder. This one is added by the first LSB is added by this half adder. Then second LSB will be added by second full adder. Then third bit will be added by this full adder, and fourth bit will be added by this adder, producing this sum. And so half adder produces sum as well as carry. This full adder will produce final sum as well as carry. So again this full adder will produce sum as well as carry, and in this way the sum and carry will move forward. So the last this is the last carry produced by full adder circuit. So this is the output of this 4-bit number. How to add the 4-bit numbers? So you remember only this diagram. No explanation is necessary for this. So this is 4-bit binary adder. Now let us move to the next important topic, that is the half subtractor. So similar to the half adder, there is a half subtractor. So in half subtractor we will subtract 2 bits. We will subtract 2 bits. So the subtraction of 2 bits will produce a borrow as well as the difference. It produces the borrow as well as the difference. So addition of 2 bits produces the sum and carry. Addition of 2 bits produces sum and carry. In the similar fashion, the subtraction of 2 bits will produce the sum, difference and borrow. So let us take the example. Suppose this A is equal to 0, B is equal to 0. If you want to subtract A minus B, so 0 minus 0, it will produce the 0 difference, and therefore there is no necessity to take a borrow. But when we take A is equal to 0 and B is equal to 1, so 0 cannot be subtracted from 1. So 1 cannot be subtracted from 0. So we have to take 1 borrow. So when we take 1 borrow, so this is that will be the 1 0. So 1 0 minus 1, it will produce the difference of 1, and therefore when 0 minus 1 will produce difference of 1, and it will take borrow 1. Now 1 minus 0, it is simple. 1 minus 0 is 1. and the borrow is 0 because 0 can be subtracted from the 1. So there is no borrow, and 1 minus 1 is 0. There is no question of taking the borrow. So borrow is required only when you are trying to subtract 1 from the 0. So when you try to subtract 1 from the 0, then borrow digit is created and the difference is 1. So this is the half subtractor subtract two binary bits, two binary digits. Half adder subtract two binary digits, that is it subtract 2 bits. So it is the only 2-bit operation, but it produces so it will have 2 inputs and it will have 2 outputs. So the inputs are A and B, and output will be the difference of the inputs A and B, and as well as borrow, So this is the half subtractor. So half subtractor is used to subtract single binary digits. They are used to subtract single binary digits or 1-bit subtraction. Here is not the 3-bit subtraction, only 2-bit subtraction is there. A minus B is there. So the borrow is created only when you try to subtract 1 from the 0. And so this is the block diagram of half subtractor. This is the block diagram of half subtractor. Now similarly, how this half subtractor works, let us see. Now this is the circuit diagram for half subtractor. So here this is the AND gate, and the input A is inverted before applying to the AND gate, and the A and B, they are directly applied to the exclusive OR gate. They are applied to the exclusive OR gate. Now when A is equal to 0, B is equal to 0, A is equal to 0, B is equal to 0. Now put the values of A is equal to 0, B is equal to 0. So if inputs A and B are 0, 0. So what will happen? So A will be inverted here. So one of the input of this AND gate will be 1. So upper input will becomes 1 because this is the NOT gate. This is the NOT gate. So if you apply 0 here, so here due to this NOT gate, 0 will be produced. 1 will be produced. So one input to the AND gate is 1, and here B is 0. So A is 0, B is 0. So A is applied to the exclusive OR gate, B is applied to the exclusive OR gate. So A is equal to 0, B is equal to 0 means both inputs are same, and therefore the output is 0. So output is 0. So output is 0. So difference is A minus B. So here it is A minus B. It is wrongly written as A plus B. No, correct. It is the sum. It is the sum A plus B, right? Now here A dot B, this is A. So due to this NOT operation, here it will be the A complement. So this is A complement dot B. So when A is equal to 0, B is equal to 0, A complement dot B is again 0 because A is 0, its complement is 1, but B is 0, therefore it is 0. So the borrow is 0. So this A dot B is the borrow, A dot B is the borrow, and this A bar dot B plus A B complement is the difference. So here is the difference. Now check the second condition. A is equal to 0, B is equal to 1. That is 0 minus 1. 0 minus 1. So apply this as the input. A is 0, B is 1. So B is 1, A is 0. So both the inputs through this exclusive OR gates are different. So it will produce a difference of 1. So the output of this exclusive OR gate is 1. So output of the exclusive OR gate is 1. That means it is difference is equal to 1. But what about the carry? So when A is equal to 0, B is equal to 1. So A is equal to 0, B is equal to 1. So that means this A complement will be 1. So this is B. So 1 into 1. So this is 1 into 1. It is 1. So the borrow signal will be 1. So borrow signal will be 1. So similarly, we can verify for other three terms here. Take the last term. This is A is equal to 1, B is equal to 1. So A is equal to 1, B is equal to 1. So this exclusive OR gate will produce a sum of 0. The output of this exclusive OR gate is 0. So difference is 0. Difference is 0. And what about the carry? Now this is 0, this is 0. So this A complement, it is 1, but this is 0. 1 into 0 is 0. 1 into 0 is 0. Therefore, the borrow is also 0. So when 1 into 1, when 1 minus 1, it is 0. 1 minus 0 is 1. 0 minus 1 is 1 with borrow 1. So this is the most important condition, which is different from the others. So this is the half subtractor. So half subtractor circuit is used to subtract only 2 binary digits. Half subtractor is used to subtract only 2 binary digits, or we can say that 2 bits. It is the subtraction, it performs the subtraction of 2 bits, and therefore there is a difference and borrow at the output there is a difference signal and the borrow signal. So this is the half adder. Now there are some situations where we are required to subtract 3 digits, where we are required to subtract 3 binary digits. So for the subtraction of 3 binary digits, because the third binary digit may be produced due to the LSB subtraction or from the higher column subtraction. So similar to the adder, ज्यावेळेला आपण 2 बिट्सचे सबट्रॅक्शन करणार तर त्याच्यामध्ये आपल्याला बारो पण मिळू शकतो आणि तो बारो आपल्याला पुन्हा सबट्रॅक्ट करायचा असतो. सो इट इज अ 3 bit subtraction. So for subtraction of 3 bits, a full subtractor circuit is used. So this is the block diagram of if we want to subtract more than 2 binary bits, we have to construct full subtractor circuit. So naturally the full subtractor circuit subtracts more than 2 binary bits. So this is the circuit block diagram. This is the block diagram of full subtractor. So full subtractor takes 2 half subtractor 1 and half subtractor 2, and 1 OR gate So first A minus B is carried out by the first half subtractor, and the difference produced is again subtracted from the carry bit, borrow bit. So if there is a borrow, then that borrow bit and the difference produced by first subtractor, they are again subtracted, and a borrow 2 and final difference is produced. So this is the one output of the subtractor, half subtractor is the borrow, and the output produced by the second subtractor is also borrow. So these 2 borrow terms are added by OR gate and it produces the final borrow. So in this way, final difference and final borrow are produced. Now see again here. So this is a half adder. Half subtractor only subtract 2 bits, and it will produce a borrow and difference. So again this difference is applied to the another half subtractor, to which there is a input as a borrow. So the borrow is again their input. So again the subtraction of these 2 bits is done in the half subtractor, and it is the final difference. It produces the final difference with borrow 2. So the borrow signal from half subtractor 1 and borrow signal from half subtractor 2, they are added by OR gate to produce the final borrow. So this is the full subtractor. This is full subtractor circuit. It uses 2 half subtractor and 1 OR gate. Now, how to implement the actual circuit? This is the half subtractor circuit that we have seen previously. This is one more half subtractor circuit, and this is the OR gate. So two half subtractor and one OR gate will perform the function of a full subtractor. So it functions as a full subtractor. So this C input is the borrow input. C input is the borrow input. So it is taken from the borrow from the first borrow digits from the LSB or from the higher column. So this is the we can verify this truth table by taking the values of A, B, C as 0, 0, 0. So when you take A is equal to 0, B is equal to 0, and C is equal to 0, so the first difference produced will be by this half subtractor difference. So 0 minus 0. So this is A is 0, B is 0. So the output of this exclusive OR gate is 0. Therefore, the difference is difference 1 is 0. So this is difference 1 is 0. Now, what is the borrow? So 0, 0. This is 1 because of the NOT gate. So at the AND gate there is a signal 1 and 0. So the AND gate is the 1 dot A dot B. So output of the AND gate is 0. So borrow 1 is 0. Borrow 1 is 0. Now this difference 1 is applied to the second half subtractor, because we have to again subtract that sum from the borrow if any. So this is the borrow signal. So borrow is a 0. C is 0 here. So here the signal C is 0. This is so the output of this second half subtractor will be the C is equal to 0. C is equal to 0, and this is suppose AB not connected here. So this is C. Okay. So this is C. This diagram is not correct here, but so it will produce C is equal to 0. So this is C is equal to 0. So this is 1 and this is 0. So output is 0. Output is 0, and 0 plus 0 is 0. So final difference is 0. Final difference is 0, and final borrow. So this borrow is 0 and this borrow is 0. So the final borrow is also 0. So you go on putting the values of A, B, C as 1, 1, 1, all these values, and verify the output. So you can easily understand how the output will be produced. Difference 1, borrow 2, final difference and final borrow. Okay. So this is the full subtractor logic diagram. Now the next is how to produce the exclusive, how to produce the inverter, or how to produce the NOT gate. How to produce the NOT gate using the exclusive OR gate. So this is the how the exclusive OR gate is converted into the NOT gate. So the one of the input of the exclusive OR gate is kept at 1. Suppose this input is always kept at 1, and if you apply 1 to the input, so because the exclusive OR gate will produce the output only when both inputs are different. So here suppose A is 0, and B is 1. A is 0, B is 1. So output will be, so when A is equal to 0, then B is equal to 1. So inputs are different, therefore output is high. So you will get 1. But if A is equal to 1, at that time B is equal to 1, A is equal to 1, B is equal to 1, and therefore the inputs are same and the output will be 0. So this circuit, that means the exclusive OR gate, can be converted. The exclusive OR gate can be converted into NOT gate or inverter by applying a high, by keeping the one variable as a high. So हे आपण एक कुठलाही एक व्हेरिएबल आपण हाय जर केला तर त्या exclusive OR गेटचं जे आउटपुट आहे, इट इज ऑलवेज द इन्व्हर्टर, इट इज ऑलवेज इन्व्हर्टेड. So this property of this exclusive OR gate is utilized to find out the ones complement of the input. So ones complement, आपल्याला माहिती आहे how to obtain the ones complement. So ones complement of a binary number can be obtained by inverting all the digits. 0 is converted to 1, 1 is converted to 0. So inverting all digits, you will get ones complement. Now suppose this is the 4-bit ones complement circuit. So when one terminal of this exclusive OR gates are tied together and it is kept high, so it is kept high, right? So it is kept high. So when this is kept high, if the common signal is low to this circuit, then the exclusive OR circuit output does not change and it remain same as the input. So if this is the low, then the values of A, B, C, D will appear at the output. So the output will not change the inputs. But if the common signal is low, so when the common signal is the 1, so when this common signal is kept high, if this is kept high, then all the bits A, B, C, D, because each gate will act as an inverter, so each input will get inverted at the output. So remember, when this high input is low, when this one of the input is low, the input signal will appear as it is, because this is low, this is low, and therefore the input will appear at the output.